Problem doso. Problem 2. So I'm in the problems now, and when I do problem 2, okay, a lot of times when I do the problems today, it's going to kind of go through a lot of this stuff. There's not a lot of stuff on here. A lot of today is problem solving. It is a lot of problem solving. I warned you. I did. I warned you. A lot of problem solving. No, I wasn't kidding. I wouldn't kid you. I'm not a goat. I wouldn't kid you because I'm not a goat. Problem 2. Consider the following reaction equilibrium process at 700 degrees. So this reaction, got hydrogen and sulfur are making hydrogen sulfide. It's at equilibrium. It says analysis shows that there are 2.5 moles of H2, blah, 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 and blah, blah, blah. So it gives me the moles of each one of the 3 gases. Okay, gases. And it tells me the flask that we have this reaction taking place in. We have a nice 12-liter flask, which would be pretty big, 12-liter flask. And we dumped our hydrogen sulfur in there, and they're making some hydrogen sulfide, and then they go settle down. It's noon at Walmart, and we have equal amounts of hydrogen sulfide breaking down and equal amounts of hydrogen and sulfur making the hydrogen sulfide. That doesn't mean we have equal amounts of them. Okay. All right, what are we trying to find? Calculate the equilibrium constant. Calculate K. So let's go ahead and calculate K. Let's write this down. So we've got 2 this plus our sulfur. These are all gases, and this has got to be balanced, so we're going to need 2 of those, H2S and gas. That should be balanced. I can look right on here. It is balanced. Okay, so we've got that. All right, so now let's go ahead and write the K value. The K value, I'll write the expression for it. Now, you can say, I hope a few of you have said, oh, they're gases, they're gases, they're gases. We can write a KP expression for this, maybe. Or we can write a KC, right? We can write either one when it comes to gases. We're going to use the one that works. What do you mean the one that works? Well, look what they gave us. Did they give us any pressures in this problem? Were we given pressures? No, we were not given pressures. We were given moles and we were given liters. That's concentration, moles per liter, moles per liter, moles per liter. So we're not going to use a KP. We are going to use a KC. KC. All right, so let's write the expression for it. They're all gases, so they all get included in our expression. We have 1 product. Don't forget your coefficient becomes your exponent. That goes over 2 hydrogens and a sulfur. Now, if I have the concentrations, I just got to throw those concentrations into the reaction, calculate away, problem solved. But we weren't given the concentrations, now were we? Well, we were given the information to find them. We were given the moles of each and the container that they're in. Now remember about gases. These are gases, and they're in a 12-liter container. Gases fill their container. So the volume of the container, therefore the volume of each gas is 12. Okay, it's 12 liters. That's the volume. And we're going to have to do 3 mole calculations, though, or 3 concentration calculations, 3 molarity calculations. 3 molarity concentration calculations. Whoa, that was hard for me to say. All right, so big M for all 3. Let's see, the first one was 2.5 moles of hydrogen. So this is the big M for hydrogen. That's 2.5 divided by 12. And the second one given is the sulfur, 1.35 times 10 to the negative 5th. 1.35 times 10 to the negative 5 divided by 12. Again, they're all in the same volume. And gases fill their container. And then the hydrogen sulfide. Down here, what was I given for that? I was given 8.7 moles of the hydrogen sulfide. 12. So let's go ahead and do that out. Calculate. I can't wait. 2.5. Do this at home, kids. Do this at home. Everybody together. Make sure you verify. Trust but verify. I've said that several times. All right, that's how many, that's the concentration. That's moles per liter. That's the concentration of the hydrogen. Concentration of the sulfur is going to be real small. 1.35. Second function exponent. Negative 5 divided by 12 is 1.125 times 10 to the negative 6. Can you see that? Yes, you can. 8.7 divided by 12 is 0.725. Okay, we now have our concentrations of all three of the gases. Okay, clear that out. And let's go put them in the equation and get this problem solved. All right, so Kc equals hydrogen sulfide. Be careful, make sure you put the right one in the right spot. Hydrogen sulfide is 0.725. 0.725. Once I start doing the math and I put things in, I get rid of the square brackets. I just put regular, good old, high-quality, made-in-America curved brackets. And down here on the bottom, the hydrogen is 0.1875. And that's squared. And then don't forget to multiply by the concentration of the sulfur, which is not squared. Nothing there, no exponent. 1.125 times 10 to the negative 6. We're going to do this out. You do it too. You do it too. 0.725 times 0.725. Enter. 0.5256. 5256. All right, then on the bottom we got 0.1875 times 0.1875 times 1.125. Second function exponent, negative 6. That's a really small number. So 3.96 times 10 to the negative 8. Okay, this K value is going to have to be really big. You have this number divided by this really tiny number. It's going to be a big value. We'll talk about that. Let's take 0.5256, divide second function, answer. And we get a syntax error. I screwed it up. Okay, we'll try it again. 0.5256 divided by 3.96, second function, exponent, negative 8. We get, whoa, big number. 1.3272727. Okay, well, let's check and make sure that we have done this problem right. That's times 1, 2, 3, 4, 5, 6, 7. I got 1.3 times 10 to the 7th. This is actually 1.1 times 10 to the 7th when I did it earlier. Okay, just let me check and verify. Did I screw this up anywhere? That's certainly a possibility. Okay, so what I'm going to do, well, you know what? The point is, here's the point. I got 1.1, I got 1.3. Okay, there was a small error somewhere, and I can go back through and I'm going to try to catch it. I'm going to stop the video in a little minute. We'll be done. But here's the thing. That's a big number. Times 10 to the 7th. That is times 10 to the 7th. That's big. What does that mean? The K value is really, really large. So that means that hydrogen gas and sulfur gas like to form hydrogen sulfide. They really like to form hydrogen sulfide. That's what that means. So you would have a lot of this and not very much of this around. Very similar to the water example I'd given you earlier. Hydrogen and oxygen like to make H2O. Okay? They really like to make that product. And that's what that K value would mean. It's a very large exponent, 10 to the 7th. What we have in front of us is not really that important. Once you get 10 to the 7th, it doesn't matter anymore. That's 10 million. Okay, so if you had if you had 11 million versus 13 million, you're still pretty rich. There's a little difference there, but you're still pretty rich. It's a big number. So we have calculated that K value. I will go back through and do the math again. I just don't want to drag you through and wait, and I'll see where that small error came. And I will be back after this. That's problem number 2, and we'll jet into problem 3 in just a minute.